Assalamualaikum and good day. In this video, we are going to look at iron-iron carbide system, or also known as iron-carbon phase diagram. In iron-iron carbide phase diagram, we are going to look at the several solid phases involved in iron-iron carbide phase diagram, phase transformation reactions, and allotropy transformation. Other than that, we are also going to look at microstructural changes on eutectoid, hypereutectoid steel, and hypereutectoid steel. I will cover this topic on 4 videos. For part 1, will be covered on iron-iron carbide phase diagram itself and on solid phases involved. And then for the second video, I will cover on phase transformation reactions. And then for the third one, allotropy transformation. And for the fourth video, I will cover on microstructural changes. So for this video, as the first part of the lesson, we will cover on solid phases involved in iron-iron carbide phase diagram. The effect of adding carbon into iron will introduce various types of steel and cast iron, which are represented by the iron-iron carbide phase diagram. This is the iron-carbon phase diagram, or also known as iron-iron carbide phase diagram. For this phase diagram, we will cover until 6.7 weight percentage of carbon in the iron. It is important for us to know what are the phases involved in iron-iron carbide phase diagram. For example, we have liquid. We also have delta phase, which are in solid phase, gamma plus liquid, gamma only in solid phase, alpha plus gamma phase, both are in solid phase, alpha phase region, which is in alpha solid phase. Then we have liquid plus cementite phase region, gamma plus cementite phase region, and alpha plus cementite phase region, which we also known as pearlite. All the phase regions that I have told you is including liquid phase. But if we look at only solid phases, we will have delta ferrite. Over here we have delta ferrite. And then we have gamma austenite phase region, which is also in solid phase. We have alpha solid phase, also known as AlphaFerrite, and Pearlite phase region. So for solid phases, we will cover on these 5 phases. These 5 phases have their own characteristic, microstructure, and properties. Other than 5 solid phases that we are going to learn, we also need to know there are 3 invariant equilibrium involved in iron-iron carbide phase diagram. The first one is peritectic, the second one we have eutectoid, and the third one we have eutectic. Please watch my video on invariant equilibrium so you will understand more on what I mean with invariant equilibrium of peritectic, eutectoid, and eutectic. Another important thing to know is on temperature and composition of any changes occurs. There are several temperatures involved. These temperatures locate all the changes occurs, and it is fixed for iron-iron carbide phase diagram. The last thing is we also need to know the composition where certain changes occurs. I circle all the important composition that we need to know in blue color pen. I repeat again, the green circle is focusing on the temperature and the blue circle focusing on composition. This temperature and composition are very important for us in order to determine the microstructure and changes occurs at certain section in iron-iron carbide phase diagram. We take a look at our first solid phase, which is delta ferrite. Delta ferrite, located at this region, is a solid solution of carbon in iron and has BCC crystal structure. BCC crystal structure also the same with AlphaFerrite in this region over here. It is a phase which exists at extreme temperature above 1400 degrees Celsius and stable only at high temperature above 1394 degrees Celsius. It melts at 1538 degrees Celsius. The maximum solubility of carbon in iron is 0.09% only at 1495 degrees Celsius. This has no real practical significance in engineering. You can read the detail on delta ferrite at this slide. This is the figure of delta ferrite crystal structure. The second solid phase that we have in iron-iron carbide system is austenite, or we also call it as Gama iron. Austenite is located at this region. Austenite is an interstitial solid solution of carbon dissolved in iron with a face-centered cubic crystal structure or FCC crystal structure. Upon heating, austenite will transform into BCC delta ferrite at 1394 degrees Celsius. The maximum solubility of carbon in austenite is 2.14%. Austenite is normally unstable below eutectoid temperature unless cooled rapidly. Austenite is a non-magnetic material. The eutectoid temperature over here is 727 degrees Celsius. You can read the info on austenite or gamma iron in this slide. This is the figure showing austenite or gamma iron crystal structure. The third solid phase that we have is AlphaFerrite. AlphaFerrite at this small region over here. It is also known as alpha iron, which is an interstitial solid solution of a small amount of carbon dissolved in iron with a body-centered cubic crystal structure or BCC crystal structure. It is the softest structure on the iron-iron carbide diagram. Stable form of iron at room temperature. As you can see, it also available at low temperature. The maximum solubility of carbon in iron is 0.022 weight% of carbon only. Ferrite dissolve less carbon than austenite. Austenite can dissolve until 2.14 weight% of carbon, but AlphaFerrite only 0.022 weight% of carbon. At 912 degrees Celsius, AlphaFerrite will transform into gamma austenite. The crystal structure also transforms from BCC become FCC. AlphaFerrite is magnetic below 768 degrees Celsius. You can pause the video and read the info on AlphaFerrite in this slide. You can also read the info on the notes given to you. This figure is showing ferrite or alpha iron crystal structure. You can compare the microstructure of alpha iron or alpha ferrite with delta ferrite. Alpha ferrite is the softest structure on the iron-iron carbide phase diagram. The fourth microstructure that we have is cementite. You can see cementite over here. It is at 6.7 weight% of carbon content in iron. Cementite is also known as iron carbide, which has a chemical formula of Fe3C. The crystal structure for cementite is orthorhombic. Cementite is an intermetallic compound. It is because a fixed amount of carbon and a fixed amount of iron are needed to form cementite. The fixed amount of carbon is 6.7 weight% and the fixed amount of iron is 93.3% of iron. As you can see in this diagram, cementite only available at here. This intermetallic compound is metastable. It remains as a compound indefinitely at room temperature, but decomposes very slowly within several years into graphite at 650 to 700 degrees Celsius. You can read the info on cementite in this slide. This figure showing pro-eutectoid cementite in the grain boundaries of a hyper-eutectoid steel. The fifth solid phase that we have is pearlite. Pearlite is available at this region. It is available below 727 degrees Celsius or below eutectoid temperature. It is resulted from transformation of austenite of eutectoid composition on a very slow cooling. Pearlite is a laminated structure or lamellar structure formed of alternate layer of ferrite and cementite. In most steel, the microstructure consists of both alpha plus cementite phases, or we call it as pearlite. It has intermediate mechanical properties between AlphaFerrite and cementite. The detail on pearlite can be read in this slide. This figure is showing pearlite microstructure, which has light background in the ferrite matrix and dark line are the cementite network. The properties of cementite is hard and properties of ferrite is soft. That's all on solid phases of iron-iron carbide system. In next video, we will see on phase transformation reaction. I hope you enjoyed the video. Thank you. Have a good day.